My name is George Sass, and I'm a staff consultant at Stress Engineering Services. I have a PhD in mechanical engineering, and I'm also a certified Category 4 vibration analyst. I have spent over 20 years of dealing with vibration problems in refineries, power plants, pump stations, and various other industrial facilities. A large percentage of these problems are related to piping vibration. Today's presentation is a general introduction to piping vibration. It is intended to help you get more familiar with the type of piping vibration problems you may encounter in a plant environment and the solutions that are conceptually available for you to mitigate them. Our agenda will be as follows. We will begin with an introduction, then we will talk about the various types of piping vibrations that can occur. Then we'll talk about overall vibration screening criteria that you can use to determine if certain piping vibration problems could be excessive. Next, we'll take a look at material fatigue, since piping usually fails due to high cycle fatigue if it vibrates excessively. Finally, we'll visit some common mitigation approaches. Sometimes the question is asked, why we even care about piping vibration? Well, some studies estimate that 10 to 15% of piping failures in onshore facilities and 20% in offshore facilities are caused by vibration-induced fatigue. The failures themselves then present significant risk in terms of personnel safety due to the potential release of hazardous and flammable process fluids. There's also an environmental impact and economic impact due to the potential production downtime as well as corrective action costs. The main reason for piping vibrations becoming an issue is that fixed equipment vibration problems are usually dealt with reactively. There are only a few situations where piping vibration issues are dealt with in the design phase. These include heat exchanger tubes, reciprocating machines, and thermal wells. For most process and power piping, the standard engineering design methods include only static loads. In other words, internal pressure, thermal expansion, dead weight, occasional volts, etc. There's no consideration for vibration and high cycle fatigue. Having said that, the Energy Institute does have some guidelines for minimizing the likelihood of piping vibration-related failures for new plant designs. Piping vibration problems can surface at any time, but there are situations when they become more likely to appear. These situations include the following: new designs where piping vibration wasn't addressed or could not be adequately predicted at the design phase, plant startups and shutdowns when flow velocities tend to vary, and after a debottlenecking or upgrade effort that resulted in increased flow velocities. Even in the situations listed on the previous slide, excessive piping vibration typically occurs due to resonance. Resonance happens when an excitation frequency coincides with the pipework natural frequency, often resulting in substantial levels of vibration, especially if the system damping is low. In the image on the left, we see an idealized single degree of freedom spring mass damper system. The dynamic behavior of a surprisingly large number of real-world systems can be approximated effectively using such a simple model. The response of this system to various excitation frequencies and damping values is shown on the right. It is clear that as the excitation frequency approaches the natural frequency, in other words, the frequency ratio between them approaches 1.0 and the damping ratio approaches 0, the response approaches infinity. In real-world systems, the damping ratio is never 0, so the response amplitude always remains finite. However, it can still get very, very large. Small bore piping connections can be particularly vulnerable to this effect. Piping vibration, unlike rotating machinery, is typically not monitored routinely using instrumentation in operating plants. Therefore, piping vibration problems are often identified initially by visual observation. The vibration is either visible itself, or it may have caused a failure that led to a visible condition, such as a leak. Sometimes piping vibration is discovered by the effect that it has on the equipment that is attached to, such as rotating machinery, which is routinely monitored for vibration. Next, we'll take a look at the various types of piping vibration. Piping vibrations can be categorized in many ways. One way to categorize them is by frequency. At the very low end of the frequency range, we have the vibration of long spans of unsupported lines, which generally take place in the 1 to 10 Hz range. Large bore piping with shorter unsupported spans and small bore branches will generally vibrate in the 10 to 300 Hz range, which is still referred to as low frequency in documents like the Energy Institute guidelines. High frequency vibrations, 300 Hz or greater, can occur on any piping geometry in the presence of a high frequency excitation source, such as a pressure drop device. Piping vibrations can also be categorized based on their vibratory mode shapes, which are related to vibration frequency. At the lower frequencies, the piping responds in a bending mode, where the center line of the piping is displaced. At higher frequencies, shell mode responses become more likely, where the piping center line stays in place and the pipe wall is deflected in waves around the circumference. What is considered high or low frequency depends on the geometry of the piping. So ultimately, what modes gets excited depends on the piping geometry and the nature of the excitation. Excitations themselves fall into three types. Tonal, where all the excitation energy is at one discrete frequency. Multi-frequency, where the excitation energy exists at multiple discrete frequencies that often come in at integer multiples. And finally, broadband, where the excitation energy covers a continuous range of frequencies. All three types may be present in a system for a given problem simultaneously. However, one type will tend to dominate for severe cases. The excitation can come from a variety of sources. The source could be, for example, mechanical forcing due to imbalance on a pump or reciprocating compressor cylinder vibration. In these cases, the machine acts as a shaker that's attached to the piping. Piping vibration can also be driven by machinery-generated pulsations. These pulses travel up and down the piping and exert forces internally on the elbows and teeth. Positive displacement devices such as reciprocating pumps and compressors inherently generate significant pulses in the working fluid, which usually need to be controlled via pulsation dampeners at the in and outlets of the machine. Centrifugal pumps and compressors generate pulses at what are called vane pass frequencies, but these pulses tend to be less intense than those from positive displacement machines. Properly attenuated pulsations from positive displacement devices and vane pass frequency pulsations usually won't become an issue unless there's acoustic resonance in the piping to amplify them. Acoustic resonance is a phenomenon where pressure waves are amplified via the formation of standing waves in an acoustic cavity, such as a piping circuit or vessel. The excitation can also be related to disturbances in the flow. Flow-induced turbulence will generate broadband excitation, typically up to around 100 Hz. Flow can also induce pulsations similar to those generated by machines if a disturbance in the flow sheds vertices at regular intervals. This can occur in any frequency range depending on the piping geometry and flow characteristics. Once again, the amplitude of the resulting vibrations typically won't become a concern unless the pulses get amplified by acoustic resonance. The last item in the list on this slide is not a source of sustained vibrations. Water hammer is a phenomenon that can be generated by sudden changes in flow velocity. For instance, by fast-acting valves in a piping system. It generates an intense transient response and can excite all the piping natural frequencies in a certain range. SCS has a separate webinar dedicated to dealing with water hammers from a fluid dynamics perspective. The last excitation source I'm going to mention is that from pressure drop devices such as orifice plates, control valves, and pressure relief valves. In gas systems, these devices can generate high-frequency acoustic excitation. This type of excitation can be quantified and evaluated based on the sound power level generated by the device. In liquid systems, the pressure drop can result in cavitation or flashing, which also generate high-frequency broadband excitation. Once a potential piping vibration problem has been identified, it is necessary to take vibration measurements to quantify it. The process of collecting this data can superficially appear to be similar to taking data on rotating machinery, but there are a number of important factors to consider in order to ensure the collection of valid and useful data. For example, piping vibration can reach double-digit levels, greater than 10 inches per second, so it is important to make sure that sensors have adequate measurement range. It is also important to make sure sensor mounting methods yield adequate frequency response. Magnet-mounted sensors will usually work, but if the piping is hot or made of stainless steel, special brackets may be needed, which will often reduce the usable frequency range. When dealing with piping vibration problems, it may be necessary to collect a large amount of data, so it is a good idea to set data analyzer frequency spans appropriately. The analyzer frequency span will dictate the necessary data sample rate, which is typically 2.5 times the frequency span. There is no need to take thousands of samples per second for a low-frequency turbulence-induced vibration problem, for example. But a low-frequency span setting might miss the high-frequency content associated with the cavitation issue. Shell mode vibration problems can present additional data collection challenges. It may not be possible to get good readings using magnet-mounted accelerometers. For excessive levels of shell mode vibration, these sensor mounts will tend to walk around on the pipe surface, so stud and adhesive mounted sensors may be required, which can be difficult to attach during operation. In these instances, a laser vibrometer can be very useful for collecting the data, since it is not limited by the vibration frequency or amplitude, or the target piping material or temperature. Of course, laser vibrometers have their own limitations. They require a certain amount of physical space near the equipment and a line of sight that is ideally perpendicular to the target surface. Once vibration data has been collected, the question immediately becomes, is the data acceptable? The easiest way to make that determination is to compare the data to a screening criteria. There are virtually an infinite variety of piping configurations out there, and as we have seen earlier, there are many different types of piping vibration problems, so it may seem impossible to come up with generic screening criteria. Still, generic screening criteria do exist, and they come in two flavors: single value or screening curve. Since they are designed to apply to many different piping configurations, they tend to be very conservative. Single value screening criteria are the easiest to use, but can be overly conservative. One of the well-known single value screening criteria comes from the ASME standard for the operation and maintenance of nuclear power plants. The ASME OM3 guidelines include a number of factors for taking into account different piping configurations. When all those factors are set to their most conservative values, the acceptance threshold becomes a ½ inch per second peak. The Russian boiler standard provides a similarly low value. Those values are in fact so low that a large percentage of piping and process plants would likely fail screening under this criterion, even if they have been operating trouble-free for decades. More reasonable single-value screening criteria are offered through a practical interpretation of the OM3 guidelines by EDI, which yielded a limit of 1.5 inches per second peak, as well as the French power and gas industries, which use 12 millimeters per second RMS, which equates to about 0.47 inches per second RMS, where RMS stands for root mean square. Single value screening criteria are easy to remember and easy to use, but they can also be easily exceeded. A better approach is to use screening curves. Screening curves take the frequency of the vibration into account, so the acceptance level changes with frequency. Many people are familiar with the screening curves on the left. These were published by EDI, and they have been around for a long time. A more recent set of curves were published by the Energy Institute, which are shown on the right. The two sets of screening curves on the previous slide are seemingly quite different, but that is mainly because they are given in terms of different units. The EDI curves are in terms of mils peak to peak, while the EI curves are in terms of inches per second RMS. If you were to convert them to the same units, they look much more familiar. Conversion on this slide was performed using a crest factor of square root 2, which assumes a perfect sine wave piping vibration response. The crest factor of a signal is the ratio of its zero to peak value to its RMS value. It is an interesting mathematical exercise to take a look at what happens if we assume a crest factor of 1.75. In other words, we assume a close to sinusoid piping vibration character, but not a perfect sine wave. As it turns out, several of the curves line up almost exactly, further emphasizing that the two sets of screening curves are not fundamentally different. Speaking of sine waves and crest factors, it is important to note that these curves were originally designed to be applicable to piping vibration where the response is in fact at a single frequency. For example, when the piping is in full-blown resonance. While that sometimes is indeed the case, there are many other cases where the response is more complex than that. In those cases, SCS recommends assigning the overall RMS level of the signal to a single effective frequency derived from the spectrum and comparing those values to the screening curves, rather than using the screening curves as a limit curves for the frequency spectrum, which can be unconservative. This slide shows the frequency spectra and overall values of mathematically constructed single mode and multi-mode signals, demonstrating the potential unconservatism associated with using the screening curves as limit curves for vibration spectra. Note how in the plot shown, the peaks in both spectra remain under the concern line, while the overall values are clearly above it. In fact, the overall value of the multimode signal even exceeds the problem level, indicating that a lot of energy can hide below the screening curves. Once a screening criterion has been exceeded, the next step is to get an idea of the dynamic stresses in the piping. This is because the vast majority of piping vibration-related failures are due to material fatigue, and fatigue is a function of alternating stresses. Note that the fatigue can take place well below the yield strength of the material in the linear portion of the stress strain curve, so the alternating stresses do not have to be exorbitantly high for this to happen. One way to get an idea of the stresses is to build a computer model of the piping. Since it is extremely difficult to analytically predict piping vibration response due to the various excitation sources, the model generally needs to be calibrated using vibration data measured in the field. For best results, use multi-channel data acquisition to help calculate the operating deflection shape of the piping, in addition to determining the frequency and amplitude of the vibration. If the stresses are found to be excessive, the computer model can also be used to test mitigation strategies for reducing the stresses. As we saw a couple of slides ago, Fatigue takes place in the linear part of the stress versus strain curve. Therefore, another possible option to obtain stresses is to measure the dynamic strain directly on the piping and relate it to stress using the Young's modulus and Poisson ratio of the material. This measurement is typically performed using strain gauges. The downside of this method is that strain gauges are not nearly as straightforward to use as accelerometers, and one has to have a pretty good idea of the location of the maximum stress for this approach to work. If strain measurements are feasible, they provide a possible shortcut to doing a full-blown fatigue assessment. It has been observed that failures seldom seem to occur below 100 microstrain peak to peak, while they tend to occur frequently above 200 microstrain peak to peak. These measurements were taken about a half-inch from the weld toes, therefore they do not include the full stress concentration effect of the welds. Introducing a strain acceptance criterion brings up the question whether it would conflict with the previously mentioned single value vibration screening criteria. Based on one data set collected in the field, keeping the vibration below 12 millimeters per second RMS, which equates to 0.47 inches per second RMS, appeared to keep the dynamic strain below 100 microstrain peak to peak, so no contradiction was found. Once the dynamic stresses have been estimated, the corresponding fatigue life estimate can be obtained from fatigue curves, sometimes referred to as SN curves. The fatigue life of the component is given by the value on the horizontal axis at which a horizontal line drawn on the SN curve at the estimated stress range intersects the relevant fatigue curve. The fatigue life of a component under high frequency vibration can be relatively short, in some cases as short as minutes or days. If the vibration is low frequency or intermittent, the fatigue life of the component can be much longer. Once it has been established that the vibration is excessive, the attention typically turns to mitigation. There are three fundamental approaches to minimize the risk of piping vibration-related fatigue failures: reducing the excitation, reducing the response, and making the piping more fatigue resistant. The first one is usually the best approach, but it is not always feasible. On the next set of slides, we will take a look at some of the solutions available for common examples of piping vibration problems. The first example will involve the very low frequency vibrations of long, unsupported piping spans. Next, we will visit some examples of low frequency vibrations, including the vibration of small bore branches, large bore lines driven by mechanical excitation, and large bore lines driven by pressure pulsations. Finally, we will look at some high frequency vibration examples, such as shell mode vibration at the compressor lobe or vane passing frequency, and broadband vibration due to control valve cavitation and acoustic excitation. Mitigating the very low frequency vibrations of long unsupported piping spans can be achieved by reducing the excitation, reducing the response, or both. The excitation can be reduced by decreasing the flow velocity or decreasing flow turbulence by applying flow smoothing. Flow velocity can be reduced by increasing the pipe size or running an additional line in parallel. Flow smoothing can, for example, be accomplished by using large radius elbows instead of mitered elbows, and using swept tees instead of regular tees. The response of the piping can typically be reduced by reducing unsupported span lengths and supporting concentrated masses, which effectively increases the stiffness of the piping. Be aware that on piping that operates hot, thermal expansion related stresses will likely increase due to the addition of additional supports. If those stresses look like they will become intolerable and supports are definitely needed, you may need to use viscous dampers instead of rigid struts. Of course, the question could be asked, why not use viscous dampers in all cases and not have to worry about thermal stresses? Well, it's because they're not maintenance-free items, so you could be trading one set of problems for another. The most common approaches to reducing the vibration of small bore connections on large bore piping involve reducing any cantilevered masses and bracing the small bore connections in all the directions that the branch can vibrate. Since the goal is to reduce the relative motion between the branch pipe and the main pipe, bracing should always be accomplished using a tieback support to the parent pipe. Never brace small bore connections to the ground or other structures. Note that they may need to be rerouted, or the configuration may need to be changed in order to facilitate effective tieback bracing. A relatively invasive but usually effective third option is to simply increase the diameter of the branch connection. Low frequency piping vibration due to mechanical excitation is typically not a problem unless the piping is in resonance. If the piping is in resonance, the best course of action is usually to stiffen the piping and thereby increase piping natural frequencies above the forcing frequency. If that is not feasible, one can try adding mass to the piping to lower the natural frequency, but never try increasing the stiffness and adding significant amount of mass at the same time, because their effects will cancel out. If the mechanical excitation is due to a machinery fault, such as imbalance, misalignment, the fault condition needs to be mitigated as well. Low frequency piping vibration due to reciprocating machine pressure pulsation is typically not an issue unless there is insufficient pulsation control at the inlet and outlet of the cylinders, or there is acoustic resonance in the attached piping, or there is mechanical resonance in the attached piping. Sometimes a triple alignment occurs between pulsation frequency, acoustic natural frequency, and structural natural frequency of the piping, which constitutes the worst case scenario, often resulting in failures. Consequently, and depending on the situation, the mitigation options are to perform an acoustic study and/or brace the piping. An acoustic study can help design better pulsation control and identify ways to prevent acoustic resonance in the pipework. The goal of bracing the piping is to tune the piping natural frequencies away from pulsation frequencies. This is sometimes easier said than done. Note that reciprocating machines generate pulsations with a lot of running speed harmonics, and the piping also has many natural frequencies. Therefore, it can be quite tricky to try to ensure that there is no alignment between any of them. And if you have a variable speed drive attached to your compressor, things get even more interesting. A common cause of piping vibration due to flow-induced pulsation is dead leg resonance. Dead leg resonance occurs when the flow past a closed side branch opening sheds vertices at the same frequency as the acoustic natural frequency of the dead leg volume. Theory suggests that a significant change in the length of the dead leg should be sufficient to prevent resonance. However, in practice, this phenomenon can be quite stubborn and persist unless the dead leg length is reduced to an absolute minimum. Minimizing the dead leg length is typically achieved by installing a valve near the branch connection itself. If the dead leg cannot be adequately shortened, an alternative solution is the installation of a barred T at the branch connection if the process allows it. A well-designed barred T can inhibit the formation of vertices at the shear layer between the stagnant fluid in the dead leg and the flow in the main line. High frequency pulsation from centrifugal and screw compressors can excite the shell mode vibration of the attached piping and vessels. This phenomenon has been observed anywhere between 300 and 2000 Hz, therefore it is in the high frequency range. It is typically accompanied by high noise levels in the area. The resulting shell mode vibration can reach well over 10 inches per second, and any small bore connection in the vicinity may not survive. It may be possible to reduce the excitation intensity by making small adjustments to the rotor design, though this is unlikely to make the problem go away entirely. The most common approach is to use a thicker pipe wall to prevent the shell mode resonance. To apply mitigation while the system is still in service, external stiffeners can be clamped on to achieve a similar effect. If there is an acoustic resonance component to the problem, inserts can help break up any standing waves that form in the piping cross-section. Cavitation at a pressure drop device due to the fluid pressure dropping below vapor pressure at the what's called vena contracta, where the flow velocity is at a maximum slightly behind the pressure drop device. These can be eliminated by installing a second valve in line with the original valve. Each valve can then be set to a larger opening to reduce the pressure drop per device while still achieving the total pressure drop required by operations. The same effect may be possible to accomplish using a multi-stage valve, which effectively integrates the function of multiple valves in a single device. Since any small bore connections near the cavitating valve are usually at the greatest risk of failure, bracing them in conjunction with a full encirclement repad or moving them away from the valve may buy you some time, especially if solving the cavitation issue is going to take an extended effort. High frequency acoustic vibration generated by pressure drop devices can be reduced by distributing the pressure drop using less restrictive devices in a tandem arrangement. In the case of control valves, it may be possible to fit the valve with a low noise trim. Reducing the flow rate by introducing a parallel line is also an option, since the energy dissipated by the pressure drop device is a function of both the pressure drop and the flow rate. Similarly to the case of cavitation, any small bore connections near the flow restriction are usually at the greatest risk of failure. Therefore, the same options to brace the SBCs in conjunction with a full encirclement repad and or relocating them away from the flow restriction apply in this case as well. I will mention that it is quite challenging to find stiff enough bracing that will work in the presence of high frequency excitation. If the source of the vibration cannot be eliminated, perhaps because it is an inherent part of the process, and the response cannot be adequately reduced, the only option left may be to make the piping more fatigue resistant by reducing the dynamic stresses in the piping. In simple terms, we'll just have to make sure that the pipework can withstand the vibration. Typically, stresses in the piping circuit will be at a maximum at a location of stress concentration due to geometry. These stress risers can be eliminated by using components such as welding tees and contoured inserts instead of weldolets, which have sharp edges. You can also grind weld gaps and toast smooth to eliminate stress risers, and so on. Switching to a thicker wall piping also tends to reduce stresses, although it's not always possible. Unless it is cost prohibitive, it is advisable to redesign the piping to be more fatigue resistant whenever possible, even if the vibrations can be reduced just for extra peace of mind. This concludes our presentation.